Next topic, logic gates. Logic gates. First, not gate. Not gate. So not gate, what it does is it is going to invert the input. And the symbol for not gate, this is the symbol for not gate. Let's say you give an input A and the output is Q. So Q is equal A bar. It is inverted. If you put the truth table means the input and the output. Okay. So the truth table, the values of A and the values of Q. If A is 0, then Q is 1. If A is 1, Q is 0. It gets just inverted. And let's look the diode circuit. We can get a NOT gate using a BJT. So NOT gate using a BJT. In a BJT, this is, let's say, plus 5 volts, and this is my input. This is the input, and this is our output. So here, VI and V out. Let's look at VI and V out. If we provide a low voltage, that is 0 volt. If this is 0 volt, this is not biased. The transistor is not biased. Then there is no IC current. Therefore, V out will be plus 5. That means when the input is low, the output is high. And when we have a higher output, there will be a IB current and there is an IC current. Therefore, V out is less than 5. That means when we provide a high voltage, the output voltage is low. Therefore, the BJT can be used as a NOT gate. Is that idea clear? Now, high voltage and low voltage, it necessarily doesn't need to be plus 5 and 0. It can be plus 5 and 0.7 also, or 5 and 1. You must be able to clearly differentiate between the two voltages. Then you can consider it as one of them as 1, the other one as 0. Do you get it? You will get that idea clear. So one of the high voltage is 1, the other one will be 0. For binary 0, it necessarily doesn't need to be 0 volt. It can be 0.7 volt or it can be 1 volt. It has to be low. Okay, that is the idea. Next gate is the AND gate. We also can have, this is a diode circuit, I mean electronic circuit, right? We also can show a NOT gate using a electrical circuit. Okay, there what should happen is now we have a bulb. We have a bulb, and here we have a switch. Now, if this switch is off, this bulb is on. If this switch is on, this bulb is off because this one becomes short circuit. So we can show NOT gate using a electrical circuit also. Okay. So here switch and bulb. Switch, bulb. Switch is open. Switch is open, bulb is on. Switch is closed, bulb is off. The opposite is happening. Usually when you on the switch, the bulb should light up, but here it is the opposite. Okay. And next there is the AND gate. AND gate. This is the symbol for AND gate. Here, let's say we have two input A, B, and the output is Q. So Q is equal A dot B. If we draw the truth table, this time we have two inputs. So if there is two input, there are four possible combinations. So A, B, and Q. How to find how many combinations is possible? That is 2 times how many input do we have? 2. So 2 to the power 2. If there is 3 input, it's 2 to the power 3. If there is 4 input, it's 2 to the power 4, and so on. So here we have only 2 input. Therefore, there are 4 possible inputs, 4 possible combinations. So in that 4 possible combination, this is how we fill. First half, we fill with 0. The second half, we fill with 1. And here, from this, half is filled with 0. The other one is 1. 0, 1. Now, 0 and 0 is 0. 0 and 1, still 0. 1 and 0, 0. 1 and 1, it's 1. And what is the electrical circuit for this AND gate? We have two switches. This is the voltage supply. If both the switches are closed, then only the bulb lights up. Okay, so this is the electrical circuit for AND gate. So we don't actually use the electrical circuit. In electronics, we use the electronic circuit. The electrical circuit is for you to get an idea, okay, to picture how this logical circuit can be shown. So here, when you close both the switches, only the bulb will light up. And if we get the electronic circuit, so that's the proper circuit we use. Here we use diodes. We have two diodes. And this is plus VCC. This is the output. This is plus 5. Look carefully. Here, let's take this one as input 1 or terminal A, and this one as V2 terminal B. So I'll put a table V1, V2, and V out. So first, let's keep V1 at 0. V1 is 0 volt. V2, it's at a higher voltage 5. Wait a minute. 0, 0. Initially 0, 0. 0, 5. 5, 0. 5, 5. Now, just like I fill the table, here I have filled it with voltage. So if both of them are 0, what can you tell about the diode? Is it reverse biased or forward biased? If this is 0 volt and here you have 5 volt, current can come down and it can go through this diode. Therefore, it's forward biased and the voltage here becomes 0.7. This voltage also becomes 0.7. Then V out, it is going to be 0.7. Is that clear? Now let's maintain V1 at 5 volt. V1 is at 5 volts and this is at 0 volt. Now, this diode is not biased, but the diode B is forward biased. Therefore, again the voltage here is 0.7. So, here also you get 0.7. This is also 0.7. Now, both of them are maintained at 5 volt. If both of them are maintained at 5 volt, these both diodes cannot be biased. Therefore, there is no current flow. There is no current flow. V out also becomes 5 volt. Is that clear how we fill this table? Saja and Sarah got it. Or shall I go through it once again? Next we have OR gate. I'll have copied, right? OR gate. So in OR gate, this is the symbol. A, B, and the output is Q. So Q is equal A plus B. We use addition symbol to show OR gate, A plus B. the truth table, again we have two inputs, therefore we will have four possible combinations. So that's 0 0 1 1 0 1 0 1. So 0 0, it's 0, 0 or 1, that is 1, 1 or 0, that's 1, 1 or 1, again it's 1. So if we draw the electrical circuit for this, if we switch on one of them, both the if we switch on one of the switch, the bulb has to work. So it's similar to a circuit like this. Now, if you switch on one of them, the bulb will work. If you switch on both of them, still the bulb will work. But if both are open, then it's not going to work. Now let's look at the electrical diagram. The electrical diagram, we have two diodes. This is our output, and this is V1. Let's take it as A, and this is V2 and B. Let's put down the table. V1, V2, and V out. Same way, 0, 0, 0, 5, 5, 0, and 5, 5. If I provide 0 voltage for A and B, obviously this diode cannot become forward biased. It cannot become biased. Therefore, it's 0. Let's provide 5 volt. If 5 volt is provided for this will become forward biased. So voltage over here becomes 4.3. But this is reverse biased. So still the output is 4.3. The output is 4.3. Here also it's 4.3. And if both of them are forward biased, I mean both of them are at high voltage, both of them are forward biased, then also the voltage is 4.3. So here we can consider 4.3 as high voltage. Then 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1. The number of rows in the truth table is equal to n, 2 to the power n, where n is the number of input, is the number of input. Done. Once you have completed, let me know. Next is the NAND gate. NAND gate. So NAND gate, it is actually the combination of AND gate and NOT gate. With the combination of AND gate and NOT gate. So here we know that this is AB. In between, we are going to get A dot B. So the output Q is equal A dot B whole thing bar. So here Q is equal A dot B whole thing bar. If we complete the truth table for this truth table, so we have two inputs. That means we can have four combinations: A, B, and Q. 0, 0, 1, 1, 0, 1, 0, 1. So Q is, let's write it as AB, A dot B, and Q. A dot B and Q. So A dot B is 0, 0, 0, 1. Then Q will be 1, 1, 1, 0. Because this is equal to A dot B whole thing bar. Okay. Done. Not number one. Now let's take only one input for this NAND gate. A. Then both the input is A. This input and this input is A. Therefore, out of the AND gate, we get A. And when it passes the NOT gate, it becomes A bar. This is identical to a NOT gate. Second, by passing this, by Now we have A and B as the input. So when it passes this gate, it becomes A bar. And when this passes this gate, it becomes B bar. And out of this gate, we get A bar dot B bar whole thing bar, right? So this is equal, Q is equal A bar dot B bar whole thing bar. We can write this as A bar bar plus B bar bar, and Q is equal A plus B. So this is identical to a OR gate. Is that clear? The second note. Third, let's say the input is A and B. So out of this we get as A dot B whole thing bar, and this is a NOT gate. So we get A dot B. This is identical to a AND gate. It is identical to a AND gate. So look, using a NAND gate, we can get all the other gates, right? Using combination of NAND gate, we can get all the other gate. We could get OR gate, AND gate, NOT gate. So we called NAND gate as a universal gate. From combinations of NAND gate, all the other uh, combination of NAND gate, NOT gate, NOT, comma, AND, comma, OR gates can be obtained. Gates can be obtained. Therefore, NAND gate is known as universal gate. Done noting up to the fourth point. Next, NOR gate. Saja and Shaham are noted. Should I scroll up, down? Okay, next NOR gate. So NOR gate, it is the combination of OR gate and NOT gate. So if we provide an input A, B, the output will be A plus B. A plus B whole thing bar. This is identical to a OR gate with a NOT gate. So if we give an input A, B, here we have A plus B. When it passes this NOT gate, it becomes A plus B whole thing bar. So if you put down the truth table, we get, again, we have only two inputs. Therefore, there are four possible combinations: A, B, and A plus B, and Q, which is equal to A plus B whole thing bar. So A 0, 0, 1, 1, 0, 1, 0, 1, A plus B is 0, 0, 1 is 1, 1, 1. Now we have just invert, therefore 1, 0, 0, 0. Just like we did for NAND gate, here also we can prove that NOR gate is also a universal gate. Not number one. If I give an input A, both of them are A, so A and A, it passes the NOT gate to become A bar. This is identical to a NOT gate. Note number 2, let's provide inputs A, B, therefore the output will become A plus B whole thing bar. Now let's send this one through another OR gate. Now this will act as a NOT gate, therefore the output will become A plus B, which is identical to a OR gate. Note number 3, A, B. So this will act as a NOT gate, therefore A bar. This act as a NOT gate, therefore B bar. So the output is A bar plus B bar whole thing bar. So Q is equal A bar plus B bar whole thing bar. This one could be written as A bar bar dot B bar bar, which is equal A dot B, and this is identical to a AND gate. Once you have finished, let me know. So NOR gate is also a universal gate. NOR gate is also a universal. Is also a universal gate.